welcome you all in this presentation related with the subject fundamentals of surface engineering. And we are talking about the approaches which can be used for modifying the surface properties so that tribological life of the component can be improved. And under this heading, we are talking about the processes wherein a layer of the material having the required set of the properties is deposited over the surface of the substrate for improving the tribological life of the component. And further under this category, we are talking about the thermal spray processes. So, in the last presentation we have seen that the flame spray is a very simple process where oxygen and fuel gas mixture is used for developing the coatings which offers the quite good deposition rate, uses very simple equipment, easy to handle, easy to adapt in manufacturing system. But this process which is commonly known as oxy-fuel powder spray process is a very simple process, but it suffers with some of the limitations which are primarily associated with the high heat input. So, because of the high heat input, we get a very coarse grain structure with these coatings and the low particle velocity which is attained by the powder which is being sprayed during the flame spray process, and therefore the velocity of the particles at the time of the impact with the substrate surface is very limited, which may be in the range of like say 10 to 50 meter. So, such a low velocity leads to the presence of the porosity and poor bonding between the coating and substrate. So, the porosity, poor bonding between the coating and substrate, coarse grain structure. So, because of these undesirable features, we find that these coatings like flame spread coatings are poor in terms of the mechanical properties, primarily like the hardness, and then these and because of the poor mechanical properties, especially the hardness, we find the lower wear resistance. Although it may be better than the substrate, but is still as compared to the other processes, the wear resistance offered by the flame spread coatings is lower. If the same material is coated using other processes, then that may offer much better wear resistance. So, the lower wear resistance. So, in order to overcome these limitations, some of the approaches have been developed, and these includes like the densification. So, in case of the densification, we know that the flame spread coating processes having the pores because of the low velocity. So, these because of this we find that the density of the coating is somewhat lower due to the presence of these air pockets, as well as these lower the hardness. So, so for eliminating these pores, normally some of the processes which are used like compaction, hot isostatic pressing and the rolling. So, when the flame spread coating is subjected to these processes, then of course, the density of the coating increases by elimination of these pores, and thereby it improves the mechanical properties and the wear resistance. One typical method we will taking up like the compaction. So, in case of the compaction, what we do is in case of the compaction, like the coating is like here, and during the coating itself, means as soon as the coating is deposited, we compress this coating using the suitable rollers, so that it is compacted continuously at the during the flame spraying process itself. So, such kind of the compaction or pressurization leads to the collapse of these pores and inclusions if they are present, and thereby it will be increasing the density by eliminating the pores and and fracturing the inclusions if they are there. So, this kind of the process is called compaction. So, here like say this is the substrate and this is the torch which is being used to develop the coating on the surface of the substrate. Since the coating on the surface of the substrate is being developed using the flame spray process, so because of the low particle velocity, it is having say some of these pores, and so to eliminate these pores, when a roller is passed through the over the surface of the coating which has been just developed, will also be at a high temperature. So, at high temperature it will be soft. So, when the roller will be passing over the surface of the coating under pressure, then it will be collapsing all those pores and inclusions which are there and making it more dense through the elimination of these pores. So, at the same time, since the plastic deformation is taking place, deformation is occurring at a higher temperature. So, the deformation assisted refinement also helps in deformation assisted refinement. Refinement helps in reducing the grain size. So, here we like in this particular case, say for nickel chromium coating being developed using the flame spray process, and as soon as the coating is spread, roller is compaction roller is passed using a normal load of the 200 newtons using the steel ball of the 25 mm diameter and 30 mm length. So, the diameter 25 mm and length of the roller was in this particular case say of the 30 mm, and since at high temperature there will be tendency for the coating material to stick with the roller. So, to reduce the sticking tendency of the material in the roller or coating material with the roller, the silicone lubricant was used to reduce the such kind of the sticking tendency. So, basically the idea is simple, where in just flame spread coating is subjected to the pressurization through the compaction roller and using suitable load, so that all the pores and inclusions pores are closed and inclusions are broken, and these will be reducing the extent of adverse effects because of these two undesirable features. At the same time, whenever the material is deformed at a high temperature through compaction, the deformation assisted refinement helps to reduce the grain size. In this particular case, nickel chromium boron silicon coating, which was coarser, we can see here the grain size of the nickel solid solution cell is coarser, and now after the compaction we notice that the grain size was reduced. So, this kind of the grain refinement may take place like say from 25 to 30 micrometer to 15 to 20 micrometer. So, the reduction in grain size is further expected to enhance the properties. So, if we see here the compaction is leading to the refinement of the grains, reducing the pores and increasing the density and maybe fracturing or breaking the inclusions. So, all these factors are expected to enhance the mechanical properties, and in this particular case increase in the hardness after the refinement and elimination of the pores, 30% increase in the hardness was observed, and this in turn also led to the improvement in wear resistance, 30 to 40% improvement due to the compaction. So, that is obvious part, like if the things are getting refined, pores are eliminated and the inclusions are being fractured, then that this will be simply increasing the coherency and the stability of the coatings, which in turn will be increasing the hardness, and increase the hardness will be leading to the improved wear resistance. So, this is one way of enhancing the performance of the flame spread coatings, which suffer primarily from the coarse grain structure, porosity and other and the presence of the inclusions as well as poor bonding strength. However, this process compaction may not be able to do much with the enhancement of the coating substrate bond strength. This is the remelting of the coating is the another approach wherein remelting of the flame spread coatings. We know that on the surface of the substrate, like say this coating has been deposited using the flame spraying process, which is having the coarse grain structure due to the low cooling rate. And so, in order to enhance the performance of the such kind of coating, the refinement of the grains as well as if the melting of the interface also can be facilitated using the controlled heating of the coatings, then that can also increase the coating substrate bond strength. So, in this particular approach of the remelting of the coating, since the oxy-fuel flame spray process uses the low cooling rate, offers the low cooling rate, because the process itself is of the low energy density, and energy density like say it is very low, like 15 to 100 watt per mm square. So, because of this the lot of heat is supplied, wherein there may not be melting of the substrate, but it gets lot of heat and it is preheated. So, the cooling rate offered by the substrate to the coating is very low, and that is why we get the high cooling rate. So, use of those heat sources which can offer the higher energy density, like the laser or electron beam or the TIG arc or the plasma arc, those heat sources can effectively be used. So, these heat sources are applied onto the already coated surface which developed by the flame spraying. So, this will be causing the controlled melting of the coating, either only the coating or coating can be melted with along with the substrate up to the interface, so that unnecessary dilution is also avoided. Since melting for this kind of melting using high energy density source, it needs the less heat supply for melting as compared to that of the gas oxy-fuel flame. And so, because of the high energy density, it uses the less heat input for melting, and therefore, it causes the high cooling rate during the solidification time, and high cooling rate during the solidification time reduces the solidification time, and a reduced solidification time leads to the refinement of the grain structure. So, there is a very simple logic. When the cooling rate is high, effective transformation temperature is reduced, and if a reduction in effective transformation temperature affects the nucleation and the growth rate. Suppose these are the two curves corresponding to the growth rate and the nucleation rate. So, at a higher temperature, what we see, at a higher temperature growth rate is high and nucleation rate is low, while at the low temperature growth rate is low and nucleation rate is high. So, when the cooling rate is high, the effective transformation temperature is reduced, and when we have the lower effective transformation temperature, this offers the high nucleation rate and low growth rate. So, because of the high nucleation rate and low growth rate, we find that there are a large number of nucleants and the growth occurs up to the limited extent, and a combination of these factors leads to the reduction in grain size of the coating, and which in turn reduces the grain size. So, apart from the refinement of the grain structure, if there are impurities present in form of inclusions here and there, remelting of the coating will be leading to the floating and elimination of these pores and inclusions up to the surface. So, not just the grain structure is refined, but the pores and inclusions are also eliminated. So, elimination of the pores and inclusions and refinement of the grain structure in totality is expected to enhance the mechanical performance and the tribological performance of such coatings. In this particular case, one flame spread coating of the nickel, chromium, boron, silicon deposited, this resulted in the coarse grain structure like this. And so, when this coating like say this one, when this is substrate, this is coating, and when it is subjected to the application of the remelting using the TIG arc, this resulted in the melting followed by the fast cooling, and fast cooling resulted in the very refined grain structure. So, if we compare these two grain structures, this structure is comparatively coarser than that of the one which is subjected to the TIG remelting. So, this structure corresponds to the flame spread coating of the nickel, chromium, boron, silicon material subjected to the TIG arc remelting, while this is simple the flame spread coatings in as spread condition. So, just after the flame spraying of this material, what is the structure, and when it is subjected to the TIG remelting using TIG, we get the very refined grain structure. Apart from this, if we see, if laser is used, laser is of the further higher energy density, and further higher energy density will be leading to the higher cooling rates. So, that will be leading to the further refined grain structures and improved mechanical properties. So, we can say here that either it is the laser or the TIG or the plasma arc, all these remelting of the flame spread coatings will be refining the grain structure, reducing the pores, and eliminating the inclusions if they are there. And if the controlled melting up to the substrate coating interface is carried out, it can also enhance the coating substrate bond strength. So, the controlled melting can be very useful. Controlled remelting of the flame spread coating can be useful with regard to the enhancement in performance of these coatings. The third approach of enhancing the performance of the flame spread coating is the controlled alloying. Since it uses basically the material to be coated is used in form of the powders, and which is flame is spread through the oxyacetylene flame onto the substrate after heating to the molten state and accelerating it towards the substrate at moderately high velocity. It is not very high, but it is like 10 to 50 meter per second, and then after impingement we will get the coating. So, like this is the torch, this is the flame, and here we are feeding the powder. It will be going with the flame, and in the flame it will be heated to the high temperature, and then it will be deposited onto the surface of the substrate. So, these are the the coating will be deposited in form of these splats onto the surface. In order to since the cooling rates which are experienced in the flame spread coating is low, that is why it offers the coarse grain structure. So, in order to improve the mechanical performance and the tribological performance with regard to the resistance to the wear, it will be good if the hardness can be enhanced by refining the grain structure, and therefore, as per the material which is to be applied, we will choose the suitable refiner which can be added in the coating material, so that the structure can be refined. There are various alloying elements, like for aluminum base materials, the titanium, boron kind of the elements are used as a refiner. For steels, vanadium and aluminum is used, and like say for the nickel cobalt based systems, even cerium oxide, lanthanum oxides, like rare earth materials can be used as a refiner. So, here idea is that whatever the grain structure we get after the flame spraying, if it is coarse, then the structure is to be refined. So, the coarse structure is being achieved because of the low cooling rate. So, if we add the refiners, these will promote the heterogeneous nucleation. So, these refining elements will be providing, like say this is the mass which is solidifying. So, when there is no refiner, the number of nucleations will be limited, and that is why we will be getting the coarse grain structure. And when the refiners are added, these will be providing large number of the nucleants, and which in turn will be promoting the heterogeneous nucleation and thus refining the grain structure. So, idea is to add those elements which can act as a refiner, so that the grain structure of the flame spread coatings can be refined. So, despite of the lower cooling rates, we may get the finer grain structure. So, in this particular case, say for nickel, chromium, boron, silicon coatings, in as a spread condition, the structure is coarse. So, when the like ceria is added, the varying percentage, like say from from 0 to like say this is about the hardness variation, and this is about the wear resistance variation. So, if we see the grain structure variation also comes out like this, the grains are coarse and then it gets refined. So, grain size, if we mention in the y axis, and in the x axis if we have the ceria addition, then for about 0.9% of the ceria addition, starting from 0, when there is no addition, the grains are coarser, and increasing ceria content up to some extent like 0.9% in this particular case refines the grain size. Thereafter again it starts increasing. So, if we see as there is a reduction in the grain size, there will be corresponding increase in the hardness of the material. So, the same material when subjected to the Syria addition, this will be refining the grain structure up to the 0.9% and thereafter it will be increasing. Similarly, just reverse trend is offered by the hardness variation as a function of the Syria addition, wherein increase in Syria content up to the 0.9% increases the hardness and thereafter it starts decreasing, and these values are in consistency with the grain size. And if we see this, if we see abrasive wear resistance of these coatings, then as the hardness increases, the wear decreases, which is reflecting from the reduction in the wear rate, and this reduction in wear rate is can be observed up to the 0.9% addition of the Syria, and thereafter further addition of the Syria starts means it does not help much to reduce the wear rate. So, the trend of the wear rate is reversed with the further addition. So, there is optimum value of the CD addition for refining the grain structure, for enhancing the hardness as well as reducing the wear. And so, this kind of the variation can also be noticed. This is the as spread flame spread coating of the nickel, chromium, boron, silicon material, where in the coarse means average diameter of the nickel solid solution cells is coarser as compared to the other case where nickel solid solution cells are finer under the identical conditions of the scale. So, this kind of the refinement is attributed to the heterogeneous nucleation being promoted by the favorable alloying elements. So, now I will summarize this presentation. In this presentation, I have talked about the 3 approaches which can be used for enhancing the performance of the flame spread coatings, and these were like compaction, which primarily eliminates the pores, breaks the inclusions if they are there, and in case of the remelting also helps to refine the grain structure. If the remelting is carried out using the suitable high energy density heat source, then it will refine the grain structure, eliminate the pores, as well as it will also reduce the inclusion content. Similarly, the controlled alloying elements which are facilitating the heterogeneous nucleation, then they will be refining the grain structure, increasing the hardness and improving the wear resistance. Thank you for your attention.